in our example, oh, maybe I was looking, I think I was looking at the, no, I think I was looking at the wrong equation for the stress, to find the minimum stress.
Mhm.
Where is it? Okay, yeah, so I think, so our angle, I don't know if you, in our example, the principal angle was 27 degrees, and then plus or minus 90, but you got that the minimum strain was 305.
These are 23 and some angle is the angle from the given reference frame in which we are having the minimum or maximum strain,
Right.
normal strain, okay? Because that comes from a minimization of the strain with respect to the orientation angle, okay? So you can find both a minima or a maximum.
Right. But in our
Okay.
example from
I don't
Friday,
remember now the example. I remember 23, then I don't remember the maximum or minimum values of the strain.
but our angle was 27 degrees.
Yeah, okay.
So finding the minimum strain, how did you get negative 305?
Because it's a minimum. It's a minimum value. It's negative something.
But if we're just doing, if we add,
So it is a compression. It is not just traction.
right, but
Okay.
if we just add like 27 degrees to 90 degrees,
Mhm.
right, we get 117.
Yes, but that is the angle, not the value.
Oh, okay.
You
Okay.
have to distinguish between the orientation angle,
Okay.
that is what I call alpha P principal.
Mm-hmm.
So you got alpha P and alpha P plus minus 90 degree.
And
And that
that gives you the
is
angle.
the
And then
angle.
okay.
Then to each value of these principal angles, you got the corresponding value of the strain. That could be either maximum or minimum.
Okay.
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 So in our exercise that we got is that the responding to the alpha p equal to 27 degrees, you got the
Right.
maximum strain. I don't remember the value, and the
Uh
minimum strain is for sure negative.
yeah, that makes sense. I was just um
Confusing the angle and the value of the strain.
yeah, so once we have the angle, we plug it into we have another equation to get the value.
Yeah, yeah.
Okay.
Okay.
What is that equation?
I think that is on top of the Friday's class, in which we have the strain in whatever angle direction alpha compared to the x and y. So just plug the alpha p into the main equation.
Oh, okay. Perfect. Okay.
Okay.
Thank you.
Good. Mm? Sì, farò qualcosa in laboratorio. Sto vedendo con la borsista di trovare una soluzione per mandarvi tutti. Non ve la dico ancora perché non so se riusciamo a realizzarla, però qualcosa faremo, forse in modo multimediale, adesso cerchiamo di capire. Il problema è che se voi foste tutti qui, quindi non ci fossero problemi, vi dividevo in gruppi come tutti gli anni faccio e a gruppi si scende in laboratorio e si fa l'esperienza. Non siete tutti qui per i problemi che conosciamo bene e quindi portare in laboratorio solo che qui potrebbe essere, diciamo, un privilegio che quelli che sono qui hanno rispetto a quelli che non sono qui non hanno, senza meritarsi, insomma, perché semplicemente sono qui. E quindi sto cercando di risolvere questo problema di rilievo. Quindi probabilmente tutti vedrete l'esperienza in laboratorio da remoto. Quindi magari chi viene in aula, se avete stato qui, devo ancora capire bene. È nuova anche per me, quindi sto cercando di... Fino all'ultimo pensavo che non ci fossero problemi per accedere in laboratorio, ma anche col decreto di ieri non è che facilita questa cosa, e soprattutto il numero di contagi sta riaumentando, quindi essere io il portatore sano di Covid in facoltà. Okay, I think that we can resume the class. Now, having said that about the strain measurement, so just to recap what we did for the strain measurement, we introduced the strain gauge, that is a resistive electrical resistance based device that transduce the strain into a change of resistance. The relation is, despite of all the circumstances, is a linear one for very small value of the strain. And because it is very small, in order to have a measurement of the strain, we have to use the Wheatstone bridge. We analyze the Wheatstone bridge in terms of the configuration, measuring configuration, quarter, half, and full bridge configuration. The sensitivity with the maximum dissipable power that we can have in our measuring circuit, and the maximum power has to be introduced, because if we try to increase too much the input voltage so that we can increase the sensitivity, then we can melt everything because we overheat the measuring device. Then we see some application of the strain gauges as devices that are capable to measure other physical quantities, force, stresses, strain, okay? And we made a very easy application of evaluating the principal value of the strain, okay, using the geometrical or analytical approach, and the graphical one, the more simple. Now, let's have a brief talk about the temperature measurements. Okay, so a question for you: what is the temperature? What is a temperature? The heat, yes, is a specific physical condition. That's true. Physical condition of a body that it telling me if the heat is flowing from that body to another one or is flowing from the other external body to the body itself. Okay. So it's a physical condition, that's true. What is characterizing that physical condition? No, generally speaking, for the temperature as a physical quantity, characterization. If you had to explain temperature to your brother and sister, that is related to the heat. We already discussed that, but the temperature.
It's the effect of release of energy.
Almost there. Yes, in class the solution, almost a solution, that is the temperature is the information, is an index related to the molecular activity. The higher is the molecular activity, the kinetic energy associated to the molecular activity, the higher is the temperature. Okay, so temperature is associated to the kinetic energy of a body. Okay, and actually it measures that kinetic energy. So temperature is an index of the molecular activity. Okay, we are not interested, of course, in entering into details of such a molecular activity, but let's see the overall effect, the global effect of having bodies characterized by different indexes, by different temperature. Okay, so what we would like to have when measuring the temperature, okay, is just to measure the change of the temperature with respect to a reference one, to which a change of some physical property could be measured. So we measure the temperature because we are measuring the change of the physical properties because of the change of the operating temperature with respect to reference one. Okay. So when having said that, we can say that the change of temperature is generally associated to, for example, a change of the physical condition, physical state, to a change of a chemical state as well, change of physical dimension, okay, change of mechanical properties, change of radiative properties, okay, and many other. Okay, so how can we measure the temperature? Just by measuring such a change of something, okay, physical condition or state, they're the same. chemical state, physical dimensions, mechanical properties, relative, and so on and so on. Okay. By the way, many times we are used to refer to temperature unit of measure that are both in Fahrenheit and Celsius. Here. So please remember that you can have the temperature in Celsius from the temperature in Fahrenheit by using this formula. Okay, which, oh, sorry. TF is the temperature in Fahrenheit, TC in Celsius. The way around formula is that the temperature in Fahrenheit is 32 plus 1.8 TC. Okay, just to remind you these two equations. That are not that difficult to remember. Okay, there is 32, that is the 0. Okay, in Celsius. 32 Fahrenheit is 0 Celsius. Okay. And then you have 1.8 to add, or you have to reduce 1.8. Okay, divide or multiply. However, now I would like to introduce you a bimetal thermometer that is a way of measuring the temperature using the property of the change of the physical dimensions. Okay, so the bimetal thermometer but the strain is another way. That's the physical dimensions. So let's say bimetal thermometer. As the name is suggesting, this kind of thermometer is composed by two foils of different materials. Okay, let me write that like this. We have one foil and to this foil we are having another one located just like this. Sorry, it's very bad drawing. Let me redo that. These two foils are bonded one each other. Okay, so what we got is that is foil number 1, for example, that is foil number 2. Generally, thickness T1 and T2 could be whatever. And so the properties could be chosen so that to maximize our measurement. Okay, please note alpha is the linear thermal expansion coefficient. Okay, T1 and T2 are the thicknesses, E1 and E2 are the Young modulus, okay, of the two foils. So thickness Okay. Now, what happens when we are having this bimetal thermometer that is operating at a different temperature with respect to the one that I consider when I was having when building this, manufacturing this bimetal thermometer. It happens that because the Young modulus, because the linear thermal expansion coefficients, because of the thickness, these bimetal thermometers start bending. Okay, so for example, if there is a change of temperature with respect to the reference one, the one that you consider manufacturing that bimetal thermometer, the metal thermometer is doing something like that. Or the way around. And of course, the way the metal thermometer bends depend on the properties, of course. Now, if you mechanically link this bending to a scale, for example, you have the information of the change of the temperature. Now, if you calibrate that, you have the information of the temperature as well. Okay, so for example, if you are connecting this to a scale, then you have the information of the change of a temperature with respect to the reference one. So you have the T0, the reference temperature, that is a very well-known temperature. Okay, if there is an operating condition that is at a different temperature, then we have a bending of your bimeter, and the change of this bend, so the radius of curvature, is telling me what is the change of temperature, and therefore the temperature, the actual temperature. Okay, now I'll give you some formulas that are helping you in designing this bimetal thermometer, so that you can see how the different parameters affect the measuring chain. Okay, so let me call M as the ratio between thicknesses of the foils. Okay, that is equal to Ti over Ti plus 1, for which, be careful in that, the alphas, that is the linear thermal expansion coefficient of lamina, that is on foil I, is less than the linear thermal expansion of foil 2. Okay? M is equal to the ratio of the thicknesses. So what does it mean? That name the foil having the material characterized by the linear thermal expansion alpha I, that is less than alpha I plus, and then you got the thickness. The same coefficient could be defined by referring to the Young modulus. I define another coefficient n, that is the ratio between Young modulus, that is EI over EI plus 1, for which, once again, alpha I is less than, oh, sorry, got an error. Alpha Please forgive me, and let's assume, because it's much better, Ti over Tj, and then alpha I less than alpha j. Okay, that's much easier. Okay. Sorry for that. So you have material I, material J. If I, the material I, is so that the linear thermal expansion is less than material J, then you have to take this ratio of the thicknesses and over the Young modulus in order to have the parameters M and N. Okay? Then, with that, we can define an additional parameter M1 that is equal to 1 plus M everything squared, M2 that is equal to 1 plus Mn divided by M squared plus 1 over Mn. Then we can prove that the radius of curvature of the bimetal thermometer when it's operating at a different temperature with respect to the manufacturing one, okay, R is equal to 3m1 plus m2 over 6 delta alpha delta T m1, okay, times the order of thickness. Please note the delta alpha is equal to the difference between the maximum and the minimum value of the linear thermal expansion coefficients. Delta T is T negative T0, the reference one. And finally, T is Ti plus Tj. That is the total thickness. Okay. And of course, the ratio of curvature is just this one, okay? From the geometrical point of view. Now, let's see some simplification just to have an idea of numbers, okay? So generally, what we can say is that the M parameter is practically 1. The N parameter is once again practically 1. That means that the R, the radius of curvature, is equal to 3 plus 1 over 6 delta alpha delta T, okay, times 1. And then times the thickness, that is 2/3 T delta alpha delta T, okay. So what we can say is that the radius of curvature, just to have an idea of the order of magnitude, is 2/3 thickness over delta alpha delta T. Now let's discuss what we got so far under that hypothesis. So what we got is that the radius of curvature is likely to be the smaller the possible, so that we have higher bending for a prescribed change of operating prescribed change of temperature with respect to the reference one. So what we have is that it's better to have change of linear thermal expansion coefficient delta alpha, that is the higher the possible. Okay, so it is delta alpha the higher that is possible. Okay, that means that one material should be characterized by a very small value of the linear thermal expansion coefficient, and the other one the highest possible, so that the change delta alpha difference between these two is the maximum. That's the reason why we are using INVAR as one material for such a thermometer that is characterized by a linear thermal expansion coefficient equal to 1.7 10 to negative 6 degrees to minus 1 Celsius to minus 1. Okay, and please remember that alpha could be also negative if you're using composite material. And that's okay. You help in maximizing the mechanical bending of this bimetal thermometer, and therefore increase the sensitivity with respect to temperature. Let's see an example of numbers. So we have bimetal thermometer made of steel and INVAR, that is an alloy. Let's assume that the thickness of one material is 0.5 millimeter. The total thickness is 1 millimeter. Alpha corresponding to the INVAR is the one that I already wrote. It is 1.7 10 to negative 6 minus 1, whereas the material, the thermal linear expansion of the other material, that is the steel alloy, is 20.2 10 to negative 6 degrees Celsius to minus 1. As a result, what we got is M equal to 1, N is equal to 0.75. Already made the calculations. If the reference temperature is 20 degrees and the actual temperature is, for example, 115 degrees, then what you got is the radius of curvature is 381.29 millimeter. Okay, so about 40 centimeters something. That is something that could be used in designing an additional mechanical device that is translating that bending into something that could be used to estimate the temperature. Okay. Yeah. Depends on what you're doing. So there is not the more accurate instrument or device that you can think to use, whatever. It depends on the activity that you are carrying out. So maybe this bimetal thermometer could be very useful in laboratory, but not that useful when you are out in a, let's say, hangar testing your aircraft, for example. Or it could be useful, but it is very costly. So you switch to another transducer that is a little bit more cheaper than the other one, so that you can afford a large number of these transducers to have the measurement of a temperature field in many points as possible. So depends what you're doing. Okay. But let me see. Let me show you other transducer. Then we can discuss a little bit about that. Another temperature transducer is the one that you already saw when referring to strain gauges, okay, and that is the one that we call resistance based thermometer. Okay, that is based on the change of the resistance, the electrical resistance, because we are changed the operating temperature with respect to the reference one. Okay, if you remember, we already used this relation in which R0 is the resistance at the reference temperature, delta T is T negative T0, in which T0 is the reference temperature. Okay, and gamma, this coefficient, is the coefficient of the change R with temperature. And that is measured in degrees to the -1. And this is a very nice equation because it is a linear one. We have a linear relation between the change of temperature and the change of resistance. Okay, so let me note that. R is linearly related with the temperature. Okay, and it is true close to T0, of course, okay, because it's a linear expansion, okay, from the reference temperature from T0. If you are not close in the neighborhood of T0, but you have to consider larger temperature range, then you can add an additional term to your linear expansion. Okay, so what you can say is that if T range is not small. Please, T range is the range of temperature from the reference temperature, okay? Then a quadratic expansion can be used, okay? That is RT is equal to R0, 1 plus A delta T plus B delta T squared, okay? That is your quadratic expansion. We are including two terms instead of just one. And as you can think by yourself, these A and B coefficients are experimentally evaluated and depend on the material we are using to manufacture the resistance. Okay. And remember, when we were dealing with the strain gauges, we made a comparison. Okay. And therefore, we find out that if there is a temperature change, then there was an apparent strain. Okay. Now we can have the dual effect. We can have an apparent temperature because there is a strain in your measurement. We made the example last time by comparing the typical strain gauge material and the one made by aluminum alloy. Platinum alloy. Okay, and we found out that there was a dual use of the strain gauge by using the platinum. Okay, so we have the same discussion as we already had. The sensitivity of this transducer S is equal to dR over dt, the derivative of the resistance with respect to the temperature, so the output and the input if you want, and that is equal to gamma R0. Okay, so assuming first order approximation, then the relation between the resistance and temperature is linear. Then what we got is the change of resistance is then giving me the change is equal to the sensitivity times the change of temperature. Okay, and the sensitivity is just the one that I wrote there. Okay, what is the sensitivity? For example, if the base resistance R0 is 10 ohms, the gamma coefficient is 40, 10 to negative 4 degrees Celsius to the negative 1. The platinum, if you remember. Okay. Then the sensitivity is 40 milliohm per degree Celsius. Okay. That is not that large value, but however, it is a good one. Generally, as you know, the change of resistance because of the change of temperature is measured once again by bridge circuits, measuring circuits, okay, like the Wheatstone bridge. Okay, so when using this, once again, we need a Wheatstone bridge. But this time, just to make a reference with what we already did to consider, we are not having the task of measuring the strain, we are having the task from the experimental point of view of measuring the temperature. So the Wheatstone bridge will be used in order to measure the temperature, the change of resistance because of temperature change. Okay, so different use. An additional transducer for temperature is the thermistor. Okay, okay, and that is a type of resistor. Sorry. Whose resistance varies significantly with temperature. Okay, and this variation is more so than the standard resistance. And indeed, this name thermistor is the name that is obtained by using thermal and resistor. Okay. These materials are ceramics and polymer. Okay, and they could have alpha that is negative. Okay, sorry, not alpha, the change of resistance. Okay, sorry, I don't know. So these are semiconductor having coefficient of variation of air with respect to temperature that is negative. Okay, and the general equation for that is such a resistance is R0 times E to beta 1 over T negative 1 over T0. Okay, that is generally referred to the Steinhart equation. Okay, beta coefficient, please note that is dependent on the material of course, and operating temperature. Just to give you an idea, the order of magnitude is 4000 Kelvin. And both T and T0 are given in Kelvin. Do not make typical high school mistake. Steinhardt. Sensitivity of this, take the derivative of the resistance with respect to the temperature. Okay. By the way, this is temperature T, yeah, to be sure about it. So the sensitivity is dr over dt, and that is equal to negative p r0 over t square t beta 1 over t negative 1 over t0. Okay. Now, because this sensitivity is negative, what we are having is that we have a negative change of resistance, an increase of temperature. So we can also think to use such a transducer, this thermistor, as a compensating electrical device. Because if you are putting this thermistor in electrical circuit, because of the electrical current flowing into this device, you have a negative change of resistance from this equation. Okay, we have a negative change of resistance, so we can use this effect to compensate possible positive variation of resistance because of the increase of temperature. Okay, so we can also use these thermistors as compensating device when you need that. Okay. We can also refer to the linear behavior, that is the resistance-based thermometers. Okay, just by defining a sort of gamma star. Okay, that is gamma star, that is dr over dt over r0, and that is equal to negative beta over t square e to beta 1 over t 1 over t star is 0. Okay, just to have a comparison with the resistance-based thermometer, or if you want to, a comparison with a linear behavior. Okay. By the way, if R0, that is a resistance evaluated of T0 set equal to 25 degrees, for example, could have a number of values in available off the shelf, could be 500 ohms, but also could go up to 10 mega ohms. Okay, or more, according to the different design. Of course, the higher is R0, the higher is the sensitivity of this transducer, as you can see there. Okay. If we are using these devices, these thermistor, in a temperature range that is not higher than 150 Celsius, or not less than, let's say, negative 50 negative 100 Celsius, these are okay. But for higher temperature, then we need a more sophisticated architecture for such a thermistor. Okay. So if T is in a very high temperature range, okay, so 200 and up to 1000, so the highest range, the possible range that we can consider, okay, then more complex experimental configuration is needed with respect to just one thermistor. Okay. Now, if we, just to give you some numbers, if we assume that the beta, the coefficient is 4000, as we already discussed, the T0 is 25 degrees, then we have the gamma star, the equivalent coefficient is negative 0.045. Okay. If you, it is just numbers, okay? And this value is much higher than the platinum resistance based thermometer. Okay. Experimental configuration is needed. Okay. Last remark, if we are using some semiconductor with silica, okay, so if silica and some impurity such as boron, we can have gamma that could be either positive or negative. Okay, and the change of resistance is once again a function that is fully non-linear. But we can play, when referring to semiconductors, with impurities, how many, how much, and the sign, the electrical sign of that, we can say that we can have both positive or negative coefficients, and they are very useful when using those devices for thermal compensation in whatever electrical circuit. Okay, good. That's it for today. I think that I have 3 minutes. I am 3 minutes late, so but, I mean I'm on time. Questions from home? Question from the classroom? Is semiconductor based with silicon and impurity or impurity? Based on boron. Hmm? Troppo grandi. Troppo grandi significa che vanno all'infinito, vediamo poco. Piccoli, eh? So the question is about the difference in the linear thermal expansion in the bimetal thermometer. The higher is the difference, the lower will be the radius of curvature, and therefore the more sensitive is the thermometer.
Scusi, professore,
Ok.
quindi la sensibilità aumenta quando si riduce il raggio di curvatura? Quando si
Sì.
aumenta.
Beh, lo vogliamo avere piccolo, così lo vediamo
Ah.
meglio.
Perfetto, quindi quando la curvatura aumenta.
Sì, esatto.
Ok, perfetto, grazie.